Okay, for Group 22's video, we did Archimedes' principle, density of object underwater. So fluids are a huge part of our day-to-day life, and this section basically covers will a certain object float. So getting started, you would submerge an object, and depending on what the object is made of, it would either sink or float. And incorporating physics with Archimedes' principle, this principle explains that the buoyant force equals the weight of the displaced fluid. So essentially, it's how much water weight did the object push out, and that water weight is equal to the buoyant force on the object.
Concept. When an object is submerged in a fluid, the fluid exerts an upward force on the submerged object called buoyant force. Differences in pressure at the top and the bottom of a submerged object are different, which determines the total buoyant force. The total buoyant force is the difference in magnitudes between the upward force and downward force. For an object to float, the object's density weighs less than the water displaced by the object.
Liquid exerts a force on objects immersed or floating in it. This force is equal to the weight of the liquid that is displaced by an object and is known as Archimedes' principle. The unit for our buoyant force is in newtons. For our equation, the net force on our object is the object's weight minus the buoyancy of the object. The object's weight is the mass of the object times gravity, and buoyancy is the fluid's density times the volume of the replaced fluid times gravity. When an object is put underwater, the pressure at the bottom of the object is higher than the pressure at the top of the object. Therefore, the net force is going to be upwards. So our buoyant force is density of the liquid times gravity times the volume of liquid displaced, which is the height of the liquid displaced by the object times the surface area of the object.
In our experiment, we will place a metal button in a cup of water and decide whether it will float or sink using the density of water, gravity, and a few equations. We will also be using a balance scale in order to measure the apparent mass of the metal button when it is submerged in water. So taking the metal button and placing it on a balance scale, we discover that in air the mass is 0.0025 kilograms, and in water the apparent mass is 0.0010 kilograms. Now the volume of the metal button is the mass in air subtracted by the apparent mass in water divided by 1,000. So that comes out to be 1.5 times 10 to the negative 6 meters cubed. And the density of the metal button using the volume and the mass in air is the mass in air divided by the volume. And the density turns out to be 1,667 kilograms per meters cubed. Now the density is higher or greater than the density of water, so the metal button will most likely sink. And the buoyant force is the density of water multiplied by the volume of the metal button, again multiplied by the gravity, which is 9.81 meters per second squared. And so the buoyant force altogether turns out to be 0.0147 newtons.
Concluded that because the density of the metal button is 1,667 kilograms per meter cubed, which is more than the density of water, the button sunk. Archimedes' principle is when an object is immersed in a fluid, the upward force applied by the fluid on the object is the same as the weight of the fluid displaced by the object. Therefore, if an object's density is less than that of water, the downward force will be greater than the buoyant force and the object will sink. If an object's density is greater than that of water, the downward force will be less than the buoyant force and the object will float.